In part, that's because we came to the US when I was quite young. My father being an academic, like many in the US, academics are from other countries. So we came and lived for a couple of years. So English was my first language. Returned to Ethiopia, but then we had to leave when I was 9, almost 10, because of the communist revolution, which was not kind to many intellectuals. So we came back to the US in 1976 to small town, central Minnesota, population about 2,000, where no one had heard of Ethiopia, really didn't know anything about Africa, and came also to find a younger brother that was 4 years old awaiting us. So we did not know that when my parents had left a few months before my sisters and I, that my mother was actually expecting. It was many years before I went back to Ethiopia, actually 34 years. It's really quite a long time. And that's because it was communist for much of the time. And so that made it difficult to go. But I was very pleased to be able to do so. So let me tell you a little bit about the overall research approach of my group. It is about studying fundamental properties of materials as they apply to energy technologies, and we use precise structures to follow these sort of create structures that allow us to measure the properties in a very fundamental way. And then also, if we've understood those properties in that way, we can then design and create energy technologies using precise fabrication tools. So in terms of the application areas, this is in fuel cells where you take a fuel like hydrogen and you generate electricity in a clean and efficient way. Electrolyzer, where you take a reactant like water and split it to make hydrogen so that you can store your electricity. So you're doing the splitting with electricity. General area, which people call solar fuels, which is to figure out ways to use sunlight to directly make a chemical fuel that, again, is easy for storage. And then a little work in batteries, which of course everyone knows what that is. In these properties then of interest are things like ion transport. How does an ion move through a solid? That's critical for many of these electrochemical energy technologies. We look at oxidation state of materials. We look at electrochemical reaction pathways. So what's the active site in a particular reaction of interest, for example, the hydrogen oxidation reaction or the oxygen evolution reaction. And we look at thermochemistry, which is to say, what is the phase stability of a material? What is its thermodynamic properties? And again, that relates a lot to its applicability in these devices. In terms of fabrication, we're doing a lot of thin film deposition. We then do some microfabrication to create structures like this, and in some cases also self-assembly. And again, emphasize that when we pursue these fabrication tools, it's really in service of either the measurement of fundamental properties or the design of these structures that have excellent properties, excellent performance characteristics overall, as opposed to being able to advance these technologies or methodologies inherently. So let me just say a little bit of why we're interested in syria and syria zirconia. In general, this is a material that has lots of interest across many, many different fields of physical chemistry, material science, and so on, because it is used for things like fuel cells, for solar fuel production, and in a fuel cell, both as the electrolyte and as the component that can do the hydrogen oxidation reaction, or in sometimes other hydrocarbon fuels. I'm having trouble reaching my controls here. Give me one moment. Let me try this again. Still not coming up. Okay, so I'm not able to use my laser pointer. I apologize for that, but let me continue. We use syria in the thermal catalysis world as a support for catalysts that do the cleanup of the car combustion exhaust. So that exhaust has things like volatile organic compounds and also nitrous oxides and sometimes sulfur oxides. And so the catalyst in this case has got to oxidize these organic compounds and then reduce the NOx to nitrogen. And so that means that you need a material, a catalyst that can sort of allow oxygen to come in and out. It has to be a good oxygen storage material, also has to have rapid kinetics and thermal stability. And so this is the material that's used. This is just showing an example of how we can control the structure to be able to get very good oxidation, where we're using propane as a surrogate for these volatile organic compounds. And again, the sort of well-defined structure allows us to achieve these nicer properties. Use of syria in energy conversion, that is in the case of a fuel cell where we need to have an electrolyte that has very good oxygen ion conductivity. And then when we lower the oxygen partial pressure, the conductivity starts to increase, and that's due to generation of N-type carriers, which now give us mixed electronic and ionic conductivity. This is just a demonstration of a typical power output curve that we get from our fuel cells. So this is just to put it in context for you, 1 watt per centimeter squared. Peak power is considered extremely high power densities, and this was in part possible because we were using this very nice electrolyte that's based on syria. And the other area in which we use this material is in the, as I mentioned, solar fuels. And that's to say that we can take cerium dioxide, heat it up to high temperatures. As we do that, so we go from here to this state, 1500 degrees Celsius, it releases some oxygen. That's a thermodynamically driven process. This is why we do a lot of thermochemistry measurements. And then when we cool it back down, it's thermodynamically driven to be reoxidized. And we do that in the presence of steam. The consequence of that reoxidation is that the oxygen is removed from the water molecule, incorporated into the structure of the oxide, and that consequently releases hydrogen. So we can do this cycle many hundreds of times, and each time we're able to produce hydrogen. So it's a very direct way to use solar concentration, which gets you to high temperatures to be able to use to generate a fuel. And because these two steps are temporarily separated, that means you don't have to separate the oxygen from the reduced fuel that you've generated. And here we're showing that you can do that with carbon dioxide as well. So we release oxygen, we release CO, we release oxygen, we release CO, and we've done this in this large reactor that simulates 1500 sun concentration. Okay. All right, so all of that is sort of the background, like why is this material interesting? So what I'm going to tell you now specifically is some measurements that we've done and characterization that we've done to understand the internal interfaces of this material. And then I will also talk about the external surfaces of this material. Okay, so the internal interfaces, that essentially just means grain boundaries in a polycrystalline sample, and how that's connected to what's called the space charge effect. Now, why do we care about these internal interfaces? So these are, sort of very typical polycrystalline materials. And this is our ceramic, cerium dioxide. It's doped with samarium. The fact that this is a 3+ dopant on a 4+ site gives us some oxygen vacancies here. And sorry, this should be 2- delta, not 3- delta. And what we see here is that as we increase the grain size, the overall impedance decreases. Okay, and that tells us that essentially the more grain boundaries that we have, this impedance associated with the grain boundaries is the one that gets larger. So when we have these very small grains, that impedance gets large. The impedance that's associated with the bulk transport is unchanged. It's a very small value, and it's unchanged. And so you can imagine that you want to have an electrolyte which has very high conductivity. That means low impedance. And so you want to have materials with larger grains, but you also want to avoid this interfacial internal grain boundary impedance, irrespective of the grain size. And the general consensus in the community in terms of where the origin of this impedance lies is that there's some sort of native cation excess right at the grain boundary core. And because you have a positive charge at the core, that induces a depletion of positive carriers in the regime, or in the near region to that internal, that core. And our charge carriers are oxygen vacancies, which are effectively positively charged. And so they are depleted by the presence of this very, very thin layer of positive charge. That also leads to some enhancement of the electron concentration, but that doesn't create an influence here. The key is that the oxygen vacancies are depleted, and when you've got your carriers depleted, that creates this very high impedance. Okay. All right, so that's the general community understanding of what's happening at these interfaces. So some of the questions then that we wanted to address is, can we detect this space charge region directly and confirm that it really is the reason that the grain boundaries have high impedance? And then what is the origin of the space charge effect? I mean, why are they positively charged? It seems to be that in many, many, many materials that there's this positive charge. Why can't it be a negative charge? Because if it were a negative charge, then you'd have an enhancement of the conductivity, which would be great. And we began to suspect that maybe impurities would be playing a role. So we are looking into that. And then, of course, you might also wonder, how much do the grain boundaries vary across a given polycrystalline material? There's so many different types of grain boundaries and different orientations. Is there a reason to believe that they all have the same magnitude of the space charge effect? So the way that we went after this is to create a lightly and nominally undoped syria. We're using these lightly doped syria materials to detect the electric field by electron holography, and then also characterize the chemistry by atom probe tomography. And then with our nominally undoped syria materials, we're looking at transport across by crystals that have single grain boundaries in them. Okay. Now, the reason that we use lightly and nominally, especially the lightly doped materials for doing the electron holography, is that the width of the space charge region is inversely proportional to the square root of the dopant charge here and concentration. So this is the concentration. So the smaller we make the dopant concentration, the larger the space charge width, and therefore the easier it becomes for us to detect it by electron holography. So it needs to be at least a few nanometers in thickness to be able to be detected. Okay, so here's our, what I'm going to call our ultra high purity 0.2% samarium doped syria. So again, samarium is the dopant that allows us to have some oxygen vacancies throughout the bulk of the material and therefore have a high conductivity. In this material, overall, this is our bulk response here, very similar to what I showed you for the more heavily doped system. That was a 15% doped syria with samarium. Here, the bulk impedance is very, very small compared to this very large grain boundary impedance. Now, overall, because our dopant concentration is small, we're measuring gigaohms of impedance. So you can imagine this was actually a very challenging experiment. And you can see that there are 4 orders of magnitude difference in the bulk conductivity versus the grain boundary conductivity. So these grain boundaries are very, very high resistance. Okay? So let's look at the grain boundary charge. And we're doing that by electron holography. And this is a technique whereby we have our sample that is sitting up here in our electric field. So this is done in a transmission electron microscope. And we split the beam. Some of it goes through the sample. Some of it serves as a reference. And then we bring the beam back together and create a hologram. So if any of you have seen, optical hologram, it's very similar idea, just that we're using electrons rather than photons. And now from this hologram, we are going to do a Fourier transform to reconstruct the amplitude and the phase that it changed due to the electron beam going through our sample. Of course, this requires a coherent electron beam, which our transmission electron microscope has to offer. And the amplitude, and especially the phase, in fact, is what tells us information about the electric field that the beam has to go through, and therefore tells us about the electric field generated within, or that exists within our sample. All right, so here's our material. So we just do a focused ion beam slice out of that polycrystalline sample that I showed you a couple slides ago. And we see a grain boundary here. We tilt it away from the zone axis so that we don't get additional interference effects from being right on the zone axis. And here's the reconstructed this is the hologram here. It has very nice high contrast. You can see here that ultimately gives us a phase limit of sort of sensitivity of around 0.2 volts for our sample thickness, which is around 70 nanometers. So here's the reconstructed phase and amplitude. And that grain boundary sits right here. So, and this is the edge of the sample. So out here is vacuum. And it's very hard to see in the phase diagram here, but the grain boundary sits right here. And our electric potential is directly proportional to this phase that we've reconstructed, divided by the thickness of the sample. And so here's our phase information. The amplitude gives us the thickness. And so we do a point-by-point comparison between these two sets of data and now reconstruct the voltage of the electric potential profile through our sample. And here we can see that that grain boundary, which corresponds again right to this point, does have a very high voltage compared to the background. And now we project that or integrate across the this direction of this image, and we see this very high potential here where that grain boundary sits. So this is, as I said, the first sort of direct observation of the electric charge associated with the grain boundary in an ionic conductor. We have to do a couple of corrections to get the more accurate magnitude of the space charge potential at the interface. Two things are, one is that our grain boundary is not necessarily parallel to the electron beam. So the electron beam is coming this way. This is our thin slice, our 70 nanometer slice of material, and our grain boundary could be at some arbitrary angle. So we correct for that because this makes the space charge potential that we detect a little bit smaller than it should be. And then we have a leakage into the field of the electric field, into the vacuum. And that gives us sort of an additional contribution to the voltage shift. So that gives us effectively an artifact of too large a potential that we detect at this grain boundary. So we correct for those two things. And what we see at the space charge potential that we've measured this across a number of different grain boundaries is that it varies widely. In fact, my student measured a couple of interfaces that it was undetectable. There was actually no space charge potential, and he thought that was a failure. But in fact, it's an important piece of evidence that the space charge is actually not inherent. But here's the ones for which we could detect the space charge potential. And you can see it is very, very wide range of values. Here, what I'm showing you is what we expected based on that impedance result for the macroscopic sample. And that impedance result is derived by just taking the ratio of the grain boundary, the bulk conductivity to the grain boundary conductivity and solving this little expression. And that gives us the space charge potential at the grain boundary. And the inverse of this is that it means that there's, with such a wide range of this space charge potential, means that there must be many orders of magnitude variation in the grain boundary conductivity. And so that tells us, you can infer from that basically that the current must follow sort of the easier grain boundary pathways, because there's no way that it's going across one of these huge space charge potentials. Okay, now let's look at the grain boundary chemistry. We do that by atom probe tomography. This is a technique whereby we, again, focus ion beam a sample to a very fine tip here. So you can see that this is, diameter here of less than 300 nanometers. And we're going to look at this region, the top 250 nanometers. And atom probe tomography, basically you put a very, very high electric field across the sample that causes electrons to fly off and go to your detector. You keep track of the chemical identity of those ions, as well as their location by where they land on this film. And then you can reconstruct what the sample looked like before you blew it apart. Okay. And so you have to be very lucky when you do this focus ion beam preparation that you actually end up with a grain boundary that's in this tip of material. So you have a very dedicated and motivated student, and that is possible. So here is our tip that we've sampled, and here's the, you can see it's in there, there's a grain boundary because there we have some additional elements that are not evident through the bulk of the material. Okay. So now we take that data and collapse it into a plot of concentration of various cations with distance from that grain boundary. And we account for the fact that the grain boundary is actually a little bit curved, so there's a little bit of mathematical transformation that happens here. But we see in the end that we have really a surprisingly high concentration of aluminum here, that's in red, and in black is the silicon. And there's also other species, quite a large concentration of calcium. And so if we now define this grain boundary sort of arbitrarily as being 10 nanometers wide and look at the concentration per unit volume, here's our large concentration of aluminum, fairly high concentration of silicon. This one has particularly high calcium. Here's our samarium content, and we can see that it matches exactly what we put in as the dopant, which was that 0.2%. And now let's see what we can do with this. Let me also say that if we, before I move to that, if we take the concentrations of aluminum and silicon, which seem incredibly high at this grain boundary, but average it across the overall sample, the concentration is actually very, very low. So this really is ultra pure material. Our grain sizes are quite large. We did that intentionally so that we could find, very well-defined grain boundaries. So these are about 10 micron grains. And so that means that even though there's a lot of aluminum and silicon at the grain boundaries, the average is quite small, and this really is an ultra pure sample. So let's see if we can compute if these elements really are sitting at this grain boundary, what kind of magnitude of space charge potential would that generate? What would it do for the electric field? So we have to make some assumptions of where these impurity elements sit. Aluminum and silicon sit right at the grain boundary, sort of not replacing cerium, as you might expect, because they're very small elements and they can't replace a very large cerium. And then we might expect calcium to replace cerium. It's quite soluble in cerium dioxide, and then barium as well. And we know that the samarium replaces cerium. And when we do that and we calculate the space charge potential by assigning charge essentially to all of these species, we see that in fact we get a 1.3 volt space charge potential for this grain, 0.6 volts for this grain boundary, and that would lead to this vacancy depletion in the one to the right here. And so this is certainly within the range of what we measured directly by the electron holography. And it's interesting, in this case, the reason that the voltage is small is because the calcium is basically screening the charge of the aluminum and the silicon. Okay, now that was for two different samples. It was the same sample, but each measurement was on a unique grain boundary. So now we'd like to directly correlate a single grain boundary by doing all sorts of measurements on it. So we can take the exact same grain boundary, measure the conductivity, measure the concentration of species, measure some crystallographic properties. Okay, so for that, we devise this, what we call a multimodal platform, and we deposit single bicrystals where we have a grain boundary here. Here's one syria crystal, here's another syria crystal deposited on this platform, where we now make contact through these through these two sides. And we're doing AC impedance spectroscopy, as I've shown you for the polycrystalline samples. We do linear sweep voltammetry, which just means we're doing a DC measurement. We do electron backscatter diffraction to tell us something about the orientation of these two grains relative to one another, and then secondary ion mass spectrometry to be able to get some information about the chemistry of this grain boundary. It's not as quantitative as the atom probe tomography, but we can't use this particular shape of sample in the atom probe tomography, so we use this secondary ion mass spectrometry. And all of these are non-destructive measurements, so if something didn't work, we can take it out and do it again, and so on. So it's more convenient than the electron holography and atom probe tomography. So we were lucky to be able to get some commercial bicrystals. It turns out that this company, Zirconia, makes syria fibers for insulation. And these have exactly the kinds of features that we are interested in. Here's our grain boundary. It's exactly normal to the fiber. The grain boundaries are, there's no amorphous material here. The overall impurity concentration as reported by the manufacturer is here. Again, this is much higher than the less than 20 ppm that we had in our sample, but they were selling this as a insulation material, so no need to have it be high purity. For us, this is a great sample shape to be able to find these individual grain boundaries and measure their transport properties. Okay, so first of all, here's our platform, the actual image of it, SEM image of it. And we're evaluating it first in the system without any grain boundary here. And we're doing our impedance spectroscopy measurement, and the diameter of this arc is it gives us the overall resistance that we measure here. Now we're at hundreds of gigaohms, so this is an even harder experiment. That's just because of the dimensions of the sample, and again, having a wonderfully dedicated student makes this possible. And the reason we're measuring the single crystal without the fiber in there at all is to establish that we're getting the right value of the conductivity. So if we compare that to taking that material and compacting it into a sintered bulk sample, measure its conductivity, we get the same value as we do with the two of these single crystal fibers without a grain boundary in them. So we're confident that our platform, despite the fact that we're measuring hundreds of gigaohms, is giving us the right value for the material response. And now let's look at it when we have the bicrystalline here. Well, in this case, the Xray capacitance makes it basically impossible to do a measurement with the impedance and separate out the bulk from the grain boundary response. We were able to do that before, but the capacitance is too high in this configuration. So what we do is use just the DC resistance to be able to detect the presence of the grain boundary. So this is the DC resistance of the single crystal. And now with these bicrystals, you can see that the current flux that goes through these materials is much lower and also becomes nonlinear. And this nonlinearity is another signature of the behavior, a space charge effect dominated behavior for the grain boundaries, which one would not expect to be ohmic. The bulk material, you expect it to be ohmic, and then out here at high voltage is where the electrodes start to give us some sort of response. Okay, and then finally, the electron backscatter diffraction. Actually, not finally, this is one more piece. Here is our bicrystal sitting here. This is sort of hollow underneath, so it's a little bit hard to see, and these are our posts that hold it up. And we put it into the scanning electron microscope and detect the backscatter image and are able to get the orientation of these two grains with respect to one another. And then the final piece, as I mentioned, is the SIMS experiment. And here we can see that once again, we have a rather high aluminum concentration right at that grain boundary. Okay, so I'm not going to go through all the individual samples. Let me just give you the overall summary. The overall summary is that, once again, we have a high amount of impurities of aluminum, silicon, calcium. And now we can see that there is a strong correlation between the resistance the resistivity of those individual grains with the concentration of these impurities. It's almost, directly correlated that we go, the resistance decreases as the impurity concentration decreases. These high valence impurity species then are really what's giving us this high impedance. And when we compare that also to the features of the grain-to-grain orientation, we can see that the higher the misorientation, the higher the impurity concentration. And that is also a thermodynamically expected result, because when you have a high misorientation, that's when you expect to have a high overall interfacial energy, and those grain boundaries should be the ones that are essentially more motivated to have impurities to lower the interfacial grain boundary, the overall surface energy. Okay. All right, so that's our findings then overall in terms of the internal interfaces. The grain boundary potential appears to be largely due to trace impurities. There's immense boundary to boundary variation. This impurity concentration appears to be related to crystallography. Now, there's no way that one can imagine making materials purer than what we did and have it be cost effective for any sort of application. So a future strategy then says, let's think about ways to modify the chemistry rather than further purify it. So I mentioned that having calcium, for example, mitigates that charge, and that could be then a useful strategy for lowering that impedance. Okay, so now let me turn to the external surfaces. And now we're looking at surface reaction rates where syria and its relatives are serving as catalysts or catalyst supports. If we look at this material in that context, it turns out the surface behavior has been studied a lot, especially computationally. And the conclusion from computation is that the 111 surface is has much lower surface energy than other surfaces, 110 and 100. And so you expect this to be the surface that's most displayed. However, interestingly, the 110 has the lowest energy for creating oxygen vacancies on its surface. And if you expect oxygen vacancies to facilitate catalysis, you'd like to have catalyst particles that have a lot of this 110 surface exposed as opposed to the other surfaces. So this has sort of created an entire industry of shape selective synthesis, where if you are able to create rods, they have a lot of the 011 surface, which has this ideally is most effective, has most oxygen vacancies on it. And then you can also control to create cubes and octahedra. So this is an example, not from our work, but from Overby, showing this really excellent control for the shape of the syria catalyst particles. Now, the group then looked at the rate of CO oxidation, so flowing CO and oxygen across these materials to see the production of CO2. And what they observed was that indeed the rods had the highest rate of conversion, the cubes less, and the octahedra the least. And that follows exactly the trend that you expect from this series of energies for creating vacancies on the surface. And you can convert this data into a turnover frequency per phase. And again, it looks, really exactly as predicted. However, I can tell you that this trend is not always obeyed. So this was a beautiful example of a result following the computationally predicted result, but there are many times where this trend, I could give you many examples where it goes the other direction. So we were interested in understanding these surfaces, but we're not the only ones. Let me just show you a couple of results from the literature. Some of my colleagues at Northwestern looking directly at vacancy formation by transmission electron microscopy, and there certainly are various vacancies here. This is a heroic effort where the vacancies are detected by looking at the density of electric counts here, and there are certainly vacancies on the surface. Electron energy loss spectroscopy is a way to look at the cerium oxidation state. So this is done in the transmission electron microscope, and you can see that there's a higher concentration of cerium 3+ on the surface as a consequence of reduction. And you would expect that that means that you have more oxygen vacancies. So when it's more reduced, more vacancies. X-ray powder diffraction has shown similar things, that when you go to smaller and smaller size, you get an increase in the lattice parameter. That has been attributed to an increase of the vacancy concentration because cerium 3+ is larger than cerium 4+, so it expands the lattice. And we've done some work using X-ray and photoelectron spectroscopy, which is by definition a surface sensitive technique, and observing that there is quite a bit of cerium 3+ at the surface under conditions where we know that the bulk does not have very high concentration of cerium 3+. And again, that tells us the surface is very well reduced, but it does not differentiate so far different terminations from different sides. Is the 110 different from the 100, for example? So some of the key questions that we wanted to go after then is there a difference in vacancy concentration on different facets? That's one. There's also another question that arises, which is it possible to control the vacancy concentration by controlling the bulk chemistry? And in particular, we know that doping syria with zirconia increases the bulk vacancy concentration. And we wanted to know, would it increase the surface vacancy concentration? Because if these things are all correlated, maybe this is why zirconium doping is advantageous for catalyzing reactions over syria. So the techniques then that we're going to use are to measure the surface reaction rate and by a technique called electrical conductivity relaxation. It also gives us the diffusivity, so I'll describe that result. And then we're going to look at the cerium oxidation state by X-ray absorption spectroscopy. So this ties now very much to the idea of having a light source, which allows you to do this experiment. And this, we do it in a way that by using an angle resolved configuration that allows us to measure the surface by X-ray absorption spectroscopy versus that in the bulk. And so we're going to vary the zirconium content and also vary the film termination or orientation to be able to answer some of these questions that we've posed here. So before I go into those results, let me just say a little bit about the bulk behavior of Syria zirconia system. Some of you may be wondering why the heck putting zirconium into Syria would introduce any bulk vacancies. Zirconium is 4+, cerium is nominally also 4+, so why should it do that? This is the overall phase diagram of the Syria zirconia system. I just want to say that we make sure that we stay in the cubic regime, so we're have enough Syria. We're not so heavily doping with zirconia that we get into these tetragonal phase space. And what we see here is that if you put zirconium into Syria and you measure the oxygen content overall, so that's 2 minus delta is the oxygen content in this overall stoichiometry, the amount of oxygen in the material decreases with increasing amount of zirconium. Of course, it decreases as we lower the oxygen partial pressure because that's how we're pulling oxygen out of the structure when there's not much oxygen in the gas phase. So the chemical potential of oxygen is very low. That's what causes the overall decrease as we go to the left. But as we introduce zirconium, the oxygen content also decreases. And that's true at 800, just as it's true at 1500 degrees Celsius. And we can analyze these data to get at the enthalpy of reduction. And it basically tells us that the enthalpic penalty of reducing the material decreases the more zirconium we introduce. So this is just a way, in the sense, of parametrizing these data. But if we want to understand where the origin of this lies, it apparently is due to the fact, as I mentioned, cerium is a large species when it's in the 3+ oxidation state. Zirconium, on the other hand, is quite small, and it's not very comfortable with the 8-fold coordination of the fluorite crystal structure. And in fact, that's why it does not adopt that crystal structure when it's just ZrO2. It adopts a monoclinic distortion that gives it 7-fold coordination. And in this structure, zirconium says, you know, I just really want to kick out that oxygen. I don't want to have it as a nearest neighbor. And cerium says, okay, I'll let you do that. I will change my oxidation state so that the overall material is charge balanced. And so the synergy between zirconium and cerium is what allows us to have this lower oxygen content when we introduce zirconium into our materials. All right, so let's look at the kinetic properties then of this Syria zirconium. And we're doing it by this technique, which I described or named as electrical conductivity relaxation. What we do is take our material. We know that it changes oxygen content as we change the oxygen partial pressure. And we expect that that means a change in conductivity. So I'll show you in a minute that it does. So if we do a step change in oxygen partial pressure, that induces a change in conductivity with time. So here's our step change. We introduce a step change in oxygen partial pressure right at this point in time here. And then the conductivity relaxes to a new value. So if we change that oxygen partial pressure, so increase it in that step change, this is the vacancy concentration profile. It goes from a large quantity to a lower quantity as we relax down to the new equilibrium state. And that, because we're oxidizing it, that is what's causing it to have a lower conductivity. So in this example where I'm showing oxidation. We measure this conductivity then as a macroscopically average value across this sample. And there are equations exist that allow us to fit these relaxation profiles to get the chemical, the diffusion coefficient of oxygen going in as we oxidize this, and also the surface reaction rate where the oxygen is being incorporated from the gas phase, picking up some electrons from the overall structure and being incorporated as oxygen ions. So this is the profile. We relax this behavior, fit to this profile, and extract these two terms. And we use this very small reaction chamber to make sure that the step change happens instantaneously. So we're measuring the relaxation of our material as opposed to the relaxation of this chamber. So here's the conductivity as a function of oxygen partial pressure. As I mentioned, it needs to be changing in order for this technique to work, changing with a change in oxygen partial pressure, and it does. Let's look at the relaxation about this point. So the amount of change in oxygen partial pressure that we're applying is would not show up on this plot. It falls within the range of this particular data point. So we now change the oxygen partial pressure. This is a plot of the normalized conductivity. So it's going from 0 to 1. We change the gas flow rate, make sure that nothing is incorrect in our experiment. So these should all look the same, and they do. And then I'll just show you a point here. What I wanted to mention is that the relaxation time here is about a half an hour. Our apparatus relaxes within a few seconds. So we know we're measuring the material. At this lower temperature and lower oxygen partial pressure condition, now the relaxation takes many, many hours. And we show here that it's reversible. That's important for the mathematical formalism that we use to fit to these profiles. Okay, so what do we get out of this? Well, I want to introduce one more concept, which is the normalized length of our material, which tells us basically it's a ratio of the reaction rate constant and the diffusion coefficient, and also taking into account the thickness of our sample. So when this number is much bigger than 1, it means that the diffusion coefficient is small, and that means that we can only measure the diffusion coefficient. And when the number is much bigger, much smaller than 1, that means that the surface reaction rate constant is very small, and the process now is dominated by the surface reaction. The diffusion is actually very fast, and so we don't detect it. So just by chance in our experiments, we ended up in these two regions where only one parameter dominated over the other. It wasn't by design, but by design, we were able to put a catalyst over the surface to be able to speed up the reaction rate constant and measure the bulk diffusion coefficient. Okay, so the short of it all is that when we introduce zirconia, the diffusion coefficient goes down a lot, You might say, why? Well, these vacancies that we introduced are in fact trapped close to the zirconium. So that's our interpretation of what's happening with the diffusion. Now, more important was the surface reaction constant. And here again, the rate goes down dramatically. And we conclude that once again, it's likely that the vacancies, although they're generated by the presence of zirconium, in fact, they are trapped next to zirconium, and that makes them not so useful as reaction sites. Okay. All right, let me skip that as I'm running out of time. Let me now go to the part where we're actually using X-ray synchrotron radiation. So that's looking at the surface chemistry and oxidation state. So we're doing X-ray absorption spectroscopy. This is a general picture of X-ray absorption result for cerium at the L3 edge. This is the Zanes region, and this is the XAFS region. We're going to focus on the Zanes region. And what we are showing here is the Zanes spectrum when we have fully cerium 3+. Okay? It has a nice sharp line, and it behaves in a way that we can see easily. When we introduce cerium in the 4+ oxidation state, so this is CaO2, where the cerium is fully oxidized, we see a big shift in that same spectrum. It's somewhat, what you expect. It's not a single white line. It took us some time to interpret and understand this, or actually find the old publications that showed what this is all about. Basically, there's some mixed final states that happen here, and there's some crystal field splitting that gives you this very complicated pattern. The most important thing for us was to recognize that this shoulder here is inherent to cerium 4+. It's not a consequence of some cerium 3+ existing in the material. So we had to make sure that we got that right, because the increase in this shoulder now becomes the signature of the cerium 3+ in our material. Okay. Now we detect the surface region by doing this angle resolved measurement. So if we go to very, very shallow angles, we below what's called the critical angle, we get what's called a total reflection from that surface. And now the penetration depth is only 2 to 3 nanometers if we're at this very shallow angle below this critical angle. So we do the measurement at around 23 degrees or so, or 0.23 degrees, sorry. And as a function of energy, because of course we have to scan energy, the change in that penetration depth is less than about a nanometer. So we're always staying at the top. We can also go back to a larger angle of 10 degrees so that we probe the entire film. And that allows us to, in the same experiment, essentially the same experimental conditions, look at the surface versus the bulk and compare the two. Okay? And this is a nice experiment because we can do easy termination control, because the single crystal substrate that we're using, which is yttrium-stabilized zirconia, is commercially available in all sorts of different orientations. It's relatively inexpensive because it's used for jewelry. And because we're using X-rays as opposed to electrons, we can do easy environmental control. We can have the gases flowing as needed. We can have environmental chamber for heating and so on. And we can also access the cation chemistry in the Z-resolved direction by using X-ray fluorescence. One thing that we don't know is, we're making an assumption that as we measure the cerium 3+, that it tells us everything about the vacancy concentration. So we don't know that those two are actually correlated on the surface. We expect at the high temperatures of our measurement, there's nothing absorbed onto the surface, so therefore they should be, although we don't directly prove that. Okay, let me show you the composition first, just to prove to you that when we make a syria zirconia film, that the zirconium concentration through the Z direction is flat. And we're changing the penetration depth using angle resolved X-ray fluorescence to get at the chemistry. And it's important for us to establish that there's no concentration gradient in zirconium, because that, of course, would change the behavior at the surface if it's just because we have a gradient in zirconium. And so we can see here that we don't. And then we wanted to do this in sort of a high throughput way. So we also have created a series of samples where we grew a compositionally graded film and then patterned it and measured each one of these little strips so that we can get 19 different compositions in one experiment. It's a little bit aspirational to get data from all 19. That's a lot of beam time, but we did about 10 of them. Okay, so let's now show you what the behavior of the material is. This is lightly zirconium dope, and the first thing that you can see is that that surface is far more reduced than the bulk. So this looks a lot like that cerium 3+ reference spectrum, whereas the bulk looks a lot like the cerium 4+ reference spectrum. Then we do a linear combination fitting to get quantitatively the cerium 3+ concentration, and so that's how we get those values. And now, as we change the zirconium concentration, what's quite remarkable here is that the surface concentration of cerium 3+ is basically flat, whereas the bulk concentration follows what we know from the thermogravimetric measurements. Okay, so that's quite remarkable. That we know that our analysis is justified. Our Zane's measurement reproduces the bulk values in the bulk, but in the surface, we see this incredible reduction. So over 70% of the cerium is in the 3+ oxidation state. As I said, zirconium has minimal influence. Now, the other aspect of this bulk result matching the thermogravimetric analysis or the thermodynamic results tells us that that surface reduced region is not very deep. Otherwise, it would be, summing because the Zanes can't avoid the surface region. And then the final piece is the influence of film orientation. Remarkably, what we see here is that the orientation doesn't matter. We were expecting to have a very high cerium 3+ concentration on this 110, which is supposed to be the most effective, most active surface, and we can see that it's not. And this is, again, one of those instances where a student thought, oh, the result is not interesting, they're all the same. Well, no, that's actually really, really interesting. So it's not must be something else about these surfaces that makes the 110 very active for CO oxidation. So we've begun to unravel this defect chemistry, but I would say that more remains. So to summarize then the external surface behavior, the surface is far more reduced than the bulk. The extent of surface reduction is evidently independent of zirconium content. In some instances where I didn't show it to you, it in fact declines with increasing zirconium content. The surface reaction rate decreases when we have more zirconium, suggests to us that those surface vacancies are in fact immobile, and there is no evident dependence on termination or orientation of that surface reduction extent. And with that, I want to thank you for your attention. Thank the two students who did this work, Xin Shu, who did the first part on the internal interfaces, and Weizi Yuan, who did the second part on the external surfaces. My collaborators, both on the holography, on the tomography, and then the X-ray absorption measurements, film growth, funding from the National Science Foundation, and also through Argonne's collaboration with the Northwestern Institute for Sustainability and Energy. And my group overall. I like to show this picture because it has a lovely Chicago background. It's a little bit outdated. And for many months, of course, we were doing our group meetings through Zoom, but we're delighted to be back in person now. And again, thank you for your attention. I will leave a visual summary here as I take any questions, hoping there is time for some. Thank you.
Thank you, Cecina. So any questions for the speaker? You could either raise your hand and down at the bottom, or just unmute yourself and blurt out any questions. Am I muted? Did everyone hear that?
No, we heard you, Lawrence.
Oh, okay.
I see that the leaf blower has started up, but I hope that you can't hear that in the background.
So I know that some of your samples you interrogate by neutrons, right?
Yes, not these ones in particular, but indeed we have done neutron diffraction, yeah. And unpublished quasi-electron, quasi-elastic neutron scattering. Yeah, and that's generally when we're looking at protons in materials, because of course, neutrons are great detectors of protons.
Right, right.
Sometimes using prompt gamma activation analysis, which is a great way to quantify the concentration of protons in a material or hydrogen in a material. Absolutely.
Now, do you have a clean room in your, I know Northwestern must have a clean room somewhere, but
yes.
this requires a clean room to make these samples?
For the film growth, that is done in a pulse laser deposition instrument. That is not in a clean room, but for the patterning, yes, then we do that in a clean room. And certainly this little bicrystal platform, we use that quite a bit.
Right.
The focused ion beam is not in the clean room. So yeah, it depends on exactly which experiment it's about. So we don't always use a clean room, but sometimes we do. Malik's got a question.
Thank you, Sosina, for this comprehensive indeed presentation. Sosina, is there, Cerium-3 is an F electron dominated? Do you think that those atoms who are on the surface located, is there a magnetism related effect somehow?
I mean, that's a really interesting question. So there is some, if you make syria nanoparticles, that has a very high concentration of cerium-3+, and therefore gives you a very high concentration of that 4F electron. There are people who've looked at what that means for the magnetism. You know, you do paramagnetic measurements and so on. So that's not my expertise, but it is certainly an area of interest. And you can, as I said, emphasize it by making the particles very small, so a large concentration of the cerium is in that 3+ oxidation state. Yeah.
Thank you.
Any other questions?
It's me.
Okay. Oh, I didn't see you there. Okay, go ahead.
Okay. Yeah, I also want to thank you for a wonderful talk, and it's amazing to see that you're working on such a small distance scale. If these things are industrially applicable, then they're going to have to do many cycles, and I know poisoning, it can kind of deteriorate the performance. So
Yeah.
I was wondering if there were metrics for those kind of things, and in the case of your material and the prognosis of it being industrially relevant or commercially relevant.
Right. So let's talk about a few different applications. So in terms of syria as a catalyst support, or syria zirconia as a catalyst support for for the combustion exhaust, that's actually done commercially. So it's part of the cerium dioxide does not easily get poisoned by hydrocarbons because it oxidizes them. It's very, very effective at oxidizing them. So there's really no poisoning that occurs. So that aspect is great. In terms of the thermochemical cycling, which is that very high temperature process by which we release oxygen, react with steam, and then produce hydrogen, we've cycled 500 times. And what happens is in the first few cycles, the microstructure coarsens a bit. That means you have fewer reaction sites, so you do get a slight decrease in rate. But then after the microstructure stabilizes, it's solid for 400 cycles. We got bored of doing it. And again, there's not much that poisons the surface of syria. The elements that poison it are silicon and aluminum. And we saw that in the grain boundaries as well. And so, they're ubiquitous elements, but the poisoning that they introduce is not extreme. And once you know that, then you start thinking about what you can do with it. And again, we cycled 500 times. Syria is definitely used commercially. So.
Thank you.
Okay.
That's great.
I think let's thank the speaker again. You can go
Okay, thank
to
you.
the, you can do a clap. You can do a thumbs up.
Thank you, thank you. Let's see how I
Let's see what else is under here.
Okay, thank you. I'm glad for the success of the conference. Thank you for the invitation.
Okay, thank you. So we have the breakout sessions starting, I guess we're now, and you can go to, if you probably old hat at this now, but if you go to the breakout rooms button down at the bottom of your screen, you can see the choices, the African Physical Society, the ePCCr, and the African Light Source, which if I look on the schedule, there's actually no ePCCr session this afternoon, just the African Light Source and African Physical Society.
So
we'll see you in your research.
the holding slide then. You'll see the holding slide come up.
Correct. Okay. All right. Thanks, everyone.
Maurice, I have a question to you.
Yes.
When is the session?
When is the session on what?
When it will be? So it's not anymore. It is cancelled.
The session this afternoon that's happening right now?
It is this afternoon. At what time?
Now.
Now, in the African Physical Society room?
Correct. So let's bounce over there. And I think that's the session that you can chair.
Okay, let me see if I can find something.
Go to breakout rooms.
Yes, I see breakout room, but
Click on it, and the choices will pop up. I see one of the speakers is already there. Let's see if I see another. I know at least one speaker is there.
it's breakout room in progress. So I click on it.
Yeah, it should say join or something like that.
Right, and in progress.
Yep, hit that.